So hi, Assalamualaikum and good day. So now we will proceed to our next part of chapter 2, part 1b. So we are still in a chapter sets. Alright, so the LO, you must be able to solve problem related to sets and functions. And these are the outlines. So we will have a look at equality, proper, set cardinality, power set, tuples, and also Cartesian product. Alright, so let's start it. So equality of sets, we have looked at it on what we meant with equality. Okay, if let's say we have two sets here, A and B, and we can say that these two sets are equal, and we will denote these two sets with these symbols, and this is the relationship. The sets A is said to be equal with set B if and only if for all element of X, this element of X is an element in A. If this X is an element of A, then this X will be an element of B. And if this X is an element of B, then it will be also an element in set A. Alright, and then using logical equivalence, we have that A is equivalent to B if and only if for all X, then we have this square bracket. If X is an element of A, then X is an element of B, and if X is an element of B, then X is an element of A. This is equivalent to A is a subset of B and B is a subset of A. Alright? Then let's have a look at what is a proper subset. So if let's say if A is a subset of B, but A is not equivalent to B, then we say that A is a proper subset of B, denoted with this symbol. A is a proper subset of B. Alright, so if A is a proper subset of B, then for all X, X is an if X is an element of A, then X is an element of B, and exists some element X where X is an element of B, but X is not element of A. Alright. Okay, so this is the diagram of our proper subset where this is a U denoted as a universal set, and then we have two sets here, set B and set A, and there exists some element of there exists some element in A, and that element also exists in B. Alright, and but there is also element which exists in B, but it does not exist in A. So if we have a look at the examples on here, let's say we have a set, we have an element 1, 2, 3, 5 in set A, and in set B we have 1, 2, 3, 5, 6, 7. And if you notice here in set B, okay, in set B we have 1, 2, 3, 5, which is same as element in A, but in B we have 6 and 7. So if we combine these two elements here, these two sets here, then we will get this Venn diagram. Alright, and here we can say that the A here is a proper subset of B. Why? Because all element in A exist in B, but there are some elements in B is not exist in A. Alright? Okay. So let's move to next term, which is we call it as set cardinality. So set cardinality, if there are exactly n distinct elements in S, where n is a non-negative integer, we say that S is finite. Otherwise, it is infinite. Okay, so the term for the cardinality, the keyword for the cardinality is n distinct element. So the cardinality of a finite set A, and it is denoted with D symbol, is the number of distinct elements of A. For example, here, okay, for example here we have an empty set here, so the number of elements in empty set is 0 because there is no element in empty set. So let S be the letters of English alphabet. So the cardinality of set S is 26 because it has 26 distinct elements. So the next example here, we have these sets, and this set contain 3 different elements. Alright, so the cardinality of this set is 3. So the next one, this is the set that contain an empty set. So basically this set has one element, and that element is empty set. So the cardinality of this set is 1. The set of integers is infinite because we have too many integers. Okay, so that's why the set for integers is infinite. Alright, so what is the power set? The power set is the set of all subsets of a set A, and it is denoted with PA, and this is called as a power set of A. So subset of all subset. Okay, so right. Let's say here we have a set A here, and this set A, it has two different element here. So the power set of this set is 2 to the power of n. Alright, where n is the number of elements. So in this case, the number the number of element in set A is 2. So the power set is 2 to the power of n. Hence, there must be 4 subsets of this A. Alright, so if we listed out the subset of this A, then we will get empty set, and then we will get the set that contain A, the set that contain B, and the set contain itself. Okay, alright, so tuples, the ordered n tuples A1, A2 until AN is the ordered collection that has A1 as its first elements and A2 as its second element, and so on until AN as its last element. Two n tuples are equal if and only if their corresponding elements are equal. So let's say here we have A1, A2 and until AN, B1 until BN, if and only if the value of A1 is equivalent to B1, A2 equivalent to B2, B3 equivalent to B3, then we say that these two n tuples are equivalent. Alright, so let's say here we have A1, example in red red color here, A1, A2, A3, A1 is 1, 3, 5, B1, B2, B3 is 1, 3, 5, then we can say that these two n tuples are equal because their corresponding elements are equal. So two tuples are called ordered pairs. The ordered pairs A, B, and C, D are equal if and only if A is equivalent to C, the value of A is equivalent to C, and the value of B is equivalent to D. Alright. Cartesian product. So the Cartesian product of two sets A and B are denoted with D, A cross B, and this is the set of ordered pairs A, B, where A is an element of A and B is the element of B. Hence, the Cartesian product where A cross B is equivalent to the ordered pairs of A, B, where A is in capital is a subset of A and B is a subset B. A is an element of A and B is an element of B. For example, here we have element AB in set A and element 1, 2, 3 in set B. So when we do the Cartesian product of these two sets, then what we will get is we will get an ordered pair of A1, alright, and then A2, and then A3, and then B1, B2, and B3. And then a subset R of the Cartesian product A, B is called a relation from the set A to the set B. Okay, a subset R of this Cartesian product is called a relation from set A to set B. So the Cartesian product of the sets A1, A2 until AN denoted by A1 cross A2 until AN is the set of ordered n tuples A1, A2, and where AI belongs to the capital AI for I equal to 1 until n. This is the Cartesian product when the set is, this is the Cartesian product of the sets itself. Alright, so if let's say we have A1, A2 until AN, and then we do the Cartesian product, then we will have the n tuples AI for all the Cartesian product of these sets. Alright, so what is the Cartesian product of A, B, C, where A is 0, 1, B 1, 2, and C 0, 1, 2? So what happened here, you will have the three tuples. Okay, you will have the first set is for this one. Okay. So for the first three tuples is you will get the 0 which coming from the set A, and then 1 which is coming from the first element of set B, and then 0 here is the first element of the set C. And then the following tuples, the 0 still coming from the first elements of A, and then 1 is coming from the first element of B, and then 1 here is coming from the second element of C. And then you will repeat the same process until all elements are considered. Okay, and then suppose that A has two elements 1, 2, then a relation A cross A from a set to itself is called a relation on A. Alright, so in this time we have a relation to itself. So let's say we have A by A. So what happened here is we will have A to the power of 2. Then we will have 1, 1, 1, 1, and then 1, 2, and then 2, 1, and then 2, 2. So you can try for the A3. Right? And then here, next example, what are the ordered pairs in the less than or equal to relation which contain AB if A is less or greater than B on the set of 0, 1, 2, and 3. So what happened here is you have a relation, it gives a relation here. So now we have A and B, alright? And in this case, in this relation, you can see we have two different relation actually. We have a case where A is equivalent to B, and the second case is where A is less than B. So, okay, so from this set here, let's say the set E here, so when A is equal to B, then you can say that is this happens 0, 0, and then from this from this set here, we will extract starting from the first element here. So when the case A equal to B, so we will have 0, 0, and then 1, 1, and then 2, 2, and then 3, 3. So this is for a case where A is equal to B. And what happened when A less than B? Then still we will start from the first element here. Then we will say that okay, 0 is less than B, so we can count it. And then 0 is less than 2, we take it. 0 is less than 3, we accept it. And then we move to the second element. 1 is 1 is greater than 0, then we cannot consider it. 1 less than 2, yes. 1 less than 3, yes. And then we 1, 2, okay, 1, 2, 1, 3. Then we move to the third element. Okay, 2 is greater than 0, so we not consider it. 2 is greater than 1, we are not consider it. And then 2 is greater than 3, so yes, we count it. We move to the third element. So 3 greater than 0, not count. 3 greater than 1, not count. 3 greater than 2, not count. So we will stop until here. So the ordered pairs which contain A, B with this relation only here. So these are the set. Alright, so we will have 0, 0, 1, 1, 2, 2, 3, 3, 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3.